Here we'll quickly look at acidity of positive and negative ions, metal ions, and let's look at copper ion in water. Copper ion is surrounded by 6 water molecules, forming octahedral complex compound. In turn, all these molecules are hydrated addition. When hydroxide ion approaches, it forms a complex with copper. We name it this process hydrolysis because we do not have Cu2 plus, we have COH plus cation. Of course, this cation has its stability constant, beta. Now, but what happens in fact? When OH minus is coming to copper, it does not come and replace this oxygen. It simply takes one of hydrogens. We have 6 water molecules, so we have 12 hydrogens. It takes one of hydrogens and one of waters is becoming OH. Now, instead of writing this as complexation process, we can say it's acidity process. So our Cu2 plus with 6 water molecules gave one proton to some other species and become deprotonated. So our Cu2 plus with water is an acid. Something against the rule. When you're looking at Cu2 plus, you do not see any protons, but in fact there are 12 of them. So acidity constant of this acid is dissociation constant of water multiplied by beta, stability constant. So stronger is this complex, stronger is acid. Stronger is interaction of your metal ion with hydroxide. Stronger is corresponding acid. Stronger is acidity of this metal ion solution. Let's look what happens. Alkali metals have absolutely no acidity. This is undetectable. Some possible interaction is observable at 1 molar concentration of hydroxide. Now, magnesium has some acidic properties, but not strontium or barium. But with 3 plus, yes, Sc3 plus, Y3 plus, lanthan 3 plus shows detectable acidity. When we are coming further to titanium and zirconium, they are actually strong acids, especially zirconium. When you put zirconium 4 plus ion in water, you instantaneously have in solution of a strong acid, and zirconium hydrolyzes to zirconium with 2 hydroxides at least. Same is true for all other transition metals. You have relatively strong acidity for 3 plus and weak acidity for 2 plus ions. Exception is Ag2 plus, which produces relatively strong acid, even being 2 plus, because of very strong interaction of mercury and hydroxide. 1 plus cations are all not acidic or barely visible acidity. 3 plus are very strongly acidic. Exception is 3 plus of lanthanoids that do not hydrolyze, so they are not acidic. We are looking at this main group. Among common strong acid is Fe3 plus, and relatively weak or intermediate acid is aluminum 3 plus. This is the same acidity constant as for acetic acid. So aluminum ion solution in water are acidic. If we'll go along the same period, we see that group number 1, no acidity, very weakly acidic magnesium and amphoteric aluminum with oxides, very acidic hydronium. There is some acidity in water, and you cannot go beyond OH minus. With H2S you cannot protonate it. You can have HS minus in water. Well, I do not believe in S2 minus unless you have fantastically basic solutions. So these can exist somewhere in concentrated sodium hydroxide only. If you have element O4 minus an ion, it's always neutral. It will not interact with H plus. Same true with element O3 minus. Why? Because appropriate acids will have 3 terminal oxygen atoms, and we remember that means they are strong. 2 terminal oxygen atoms, they are strong. Element O2 minus anions are weakly basic because corresponding acids are weak acids. And element O minus anions are moderately to strong basic because appropriate acids will have very little, if any, acidity. So, among common, chlorate, manganate are neutral completely. Sulfate, chromate, molybdate are weakly basic. Actually, you will not see any basicity of sulfate or chromate salts at all. So this weakly is fantastically weakly. Phosphate and vanadate show relatively strong basicity, and silicate ion is so strong base that will instantaneously react with water, forming silica gel. Doesn't exist in aqueous solutions.